Hey guys, welcome back to week 24. So last week we asked a pretty foundational question, which was given a specific loss function, what's the best possible prediction function? And we showed that under, squared error laws, the answer is the regression function. So that's the conditional expectation of y given x. And we sort of reinterpreted both linear regression and k-nearest neighbors as two different strategies for approximating that same regression function. And we also found out they were kind of, opposites of one another. So this week we'll find out that approximating that regression function locally, like k and n, is a lot harder than it sounds, once you leave lower dimensional space. So section 2.5, which is this week, is literally called Local Methods in High Dimensions, and is ESL's explanation for why k-nearest neighbors, which looked pretty intuitive and simple last week, often fails apart as you add more features or add more dimensions. All right, let's start with a reminder first. So recall, under squared error laws, the single best possible prediction at point x is a regression function, which is the conditional expectation of y given x is equal to x. Okay, so here's our familiar regression function that we want to estimate. Now, of course, the problem is that we almost never have, multiple observations sitting exactly at this x value. So we can't just average the y's at this x, the way that, the formula wants. So k and n, or k nearest neighbors, way of fixing this problem is to relax sort of at x instead as near x, and swap the true expectation here as a sample average. These happen to be the closest. Alrighty, so here's how KNN estimates that regression function. It basically takes the sum of all the y values around your point, which is in the neighborhood, and then divides by k, which is the size of the neighborhood, and so you get an average. So again, KNN is just substituting a local average for a conditional one, and that substitution is only as good as the neighborhood it's built on. So this neighborhood n of k of x. So if n of k of x is genuinely close to x, this is a solid approximation, right? And if it isn't close, the approximation breaks down before the averaging, even enters the picture. So this is exactly the question we're kind of putting pressure on today. Alrighty, so here's the setup. Suppose our input data x is spread uniformly over p-dimensional unit hypercube. The hypercube is, you probably know, but it's the generalization of the unit square or unit cube to p features. So say you want to base a prediction on a neighborhood containing some fraction r of the data, the nearest, let's say, 10%, for example. Then how big does that neighborhood need to be? Well, because the points are uniform, capturing a fraction r of all the data means capturing a fraction r of the volume of the hypercube, right? And so if we build that neighborhood as a smaller cube centered in the middle of the space, or even anywhere in the space, we can ask how long does each edge of that cube need to be? And since the cube is in n or p dimensions, we know that the volume of a cube is just the side length multiplied by itself by however many dimensions they are. So if 3 dimensions, it's r cubed. If it's p dimensions, it's r to the p. And so the side length must be the volume square root with base p. Okay, so here's our picture here. And we're just assuming here that the edge length is 1, so it just simplifies. So you can imagine this cube in higher dimensional space. I've sort of drawn it here in 3-dimensional space, but imagine 4, 5, all the way up to 10, or however many arbitrary dimensions. And then we ask, say we want to capture 10% of the data in our local neighborhood. The question is, how big of the neighborhood do we need to be relative to the volume of the cube to capture 10% or whatever of our data within that neighborhood? Okay, so let's look at first at, let's say the dimension of this hypercube is 10. So in this case, let's figure out the length of the side of such a cube that would hold 10% of the data. Okay, so we are in 10-dimensional space and we want to capture 10% of the data. And so it turns out that our edge length, so the length of this cube, this face here, must be 0.8 or 80% the size of this cube. And it doesn't get much better if you sort of relax the number or the volume of data that you want to capture all the way down to 1%. If you want only 1% of data, you still need a side length of 0.63 or 60% the size of the entire space. So that's pretty massive. Okay, so that sounds pretty bad, but let's think about why that actually hurts a method like k-nearest neighbors. So the entire premise of the local method is that the points close to x, our point of interest, which is our neighborhood, those x values has a y value that is actually reflecting of the potential y value that x could take. So in other words, points close to x should have f values close to f of x. That's the only reason averaging nearby y's is supposed to approximate f of x well. But if we're reaching a modest fraction of the data, it means reaching out to 80% of the range on every axis. That points you're averaging aren't even close to x anymore in any meaningful sense. They're scattered across almost the entire space, possibly from regions where f looks nothing like x. So the averaging stops approximating local behavior and starts approximating something closer to the global average. So that's actually important. Hold on to that. That's exactly the mechanism behind the bias that we're going to look at later. So here's one more diagram to sort of hit it home as you increase your dimensions here. So in just 2 dimensions, so you just have a square, to capture 10% of your data, then your edge length needs to be 32% the size of your data range. On the other hand, if you want the same 10% for dimension 10, that edge length must be closer to 80. So far we've sort of looked at the problem with local methods as a question of how big does a region need to be to hold a fraction r of the volume. So now I'm going to ask a slightly different question. How much volume is left near the center once we've shrinked inward by some amount? Let's call it epsilon. All right, so on the top right is an argument for what happens as dimension goes to infinity. Okay, so how can we make sense of this? Well, first of all, let's see that B of P is a unit ball in p-dimensional space. Okay, so what we're doing is we're taking the ratio of the volume multiplied by some constant where epsilon is a small value. So looking at my very bad diagram here, this top term here represents the sort of inner volume moved by some epsilon. So you're slightly within that region, and the denominator is the original full volume, and so you're looking at the ratio between the two, and of course these terms cancel and you get 1 minus epsilon multiplied p times. So what happens is as p goes to infinity, meaning as you increase your dimensions more and more, this term obviously goes to 0 because this expression inside the exponent is less than 1. Okay, so what does this mean? Well, this means that as their dimension grows, virtually none of the ball's volume is left near the center. It all gets pushed to a sort of thin shell hugging the surface. In other words, this ratio here of the inner circle divided by the ratio of the outer circle goes to 0. And that can only go to 0 when this outer circle has much, much more volume, than this inner circle here. So that's saying that the volume, most of the volume is on the edge here. Most of the volume is on the edge. Okay, so hopefully that makes sense, but let's make that more concrete. So let's suppose n points are drawn uniformly from a p-dimensional unit ball instead of a hypercube centered at the origin. Now let's define this distance function, which takes input p or dimension and n, the number of samples, as the median distance from the origin to the single closest of these endpoints. So here's what we mean is that we sample endpoints from the some hyper sphere, and we want to find the distance between the smallest point closest to the origin. Okay, and there's this handy formula, which gives the equation in terms of n and p, so we can just plug in numbers. Okay, so plugging in again for dimension is only 10 and 500 data points. We see that the closest point to the center, on average, is already more than halfway to the edge of the ball. So I want to say that again because that's really, really remarkable. We have 500 data points in only 10 dimensions. 10 dimensions is not that much in machine learning, but we have a uniform distribution on this hypersphere. And what this is saying is that across all of the 500 data points, the closest point to the center is on average already more than halfway to the edge of the ball. So that's saying that most of the points are closer to the edge than even closer to the center. Now you might be wondering, why does this matter for prediction? Well, the reason is that there's a difference between interpolating and extrapolating. When you're inside a cloud of training data, points surround you sort of on every side. So if you have a lot of points here and your point of interest is this location here, these points surround you on each side of that point. So the errors tend to kind of average out. It's interpolation, and that's forgiven. On the other hand, near the boundary here, like these points seen in the picture, we don't see points all around them and all sides. Why? It's because the points are near the boundary. So you only have neighbors on one side. There's nothing outside to check your assumptions against. And the true function is, kind of free to do something you've never really observed before. So at 10 dimensions, this typical point isn't, occasionally near the edge. It's already more than halfway there by default. So almost every prediction becomes an extrapolation problem instead of an interpolation problem. And extrapolation is exactly where local averaging is least trustworthy. Okay, so to recap two problems in high dimensions, neighborhoods have to get big to hold enough data, and the data that's out there is itself concentrated near the outer edge rather than the center. Combined, local averaging ends up learning on points that are far away from X, or point of interest, and structurally pulled towards the boundary, and usually sitting on only one side of the query. Okay, so let's look at an example using a local method we are already familiar with, which is k-nearest neighbors. All right, so let's for this example, let's assume that there's no noise at all. So the true function is already known, defined here, and it's a sharp peak centered at the origin. Alrighty, and if you plot it, it would look something like this. If x is equal to 0, so at the origin, the value at f would be 1, right? And it would quickly fall off or taper off to 0 as you increase your distance away from that origin. That's what this 2 norm represents. There should be a 2 here. Now our estimator is k and n, specifically when k is a 1. So what this means is that to find the closest training point at x is equal to 0, what we do is that we find the closest point to x equals 0. So some point closest to the origin in our training set. And then we just assign our predicted value at that exact value that that point took. So for example, if the closest point, let's say, x1, let's say our closest point has this, coordinates. So it's very close to 0 on the x-axis and very close to 0 on the y-axis. And therefore, if you plug this in, I'm just going to make up number here. So our predicted value at 0, and that turns out to be pretty close to the true value of 1. So let's try to understand how good this estimator is. We can decompose this mean squared error. So let's start with the definition. So the mean squared error is just the expected value over the difference between your predicted value and the actual value squared. Now we can write this out as follows. We can include the term expected value y hat, and we can subtract and add it, so we're not changing the equation. And just to simplify, let a be this term, and let b be this term. Okay, now we just have to expand it out. Now notice that our b term here is just a constant, right? It doesn't depend on any particular training set, only its expectation. So this cross term cancels out here. So you can, since a and b are independent, so distributing the expected value on a and b, you take the expected value a, which is this term, but you already take the expected value y hat. So all you do is take the expected value of y hat here, and then of course, this is 0. They cancel out. Okay, what we're left with is we're left with the expected value of a squared and the expected value of b squared. Now let's look at a again. So a is the y hat minus the expected value of y hat. So this is how much vary our prediction. Our prediction is, depending on the average value of our prediction. So you can think of it as a variance of our prediction. On the other hand, b is the expected value of our prediction minus the actual true value at that point. So the bigger the difference, the bigger the bias. And so this is the bias term, and so we have the bias squared here. So this is you might recognize it as the bias of variance decomposition, but not quite because we again assumed that we know the true function, and the true function does not have any variance. So this is the complete bias variance decomposition for this particular problem. We'll see it in the more general problem later, but this gives you a hint. Okay, so in any case, now we should ask, how big are these two terms, and how do they behave as p grows or dimension grows? Now first, notice that unless the nearest neighbor happens to land exactly at 0, 0, or exactly at the origin, so for some x is not equal to 0, our estimate will of course be less than the true value of 1. Right? We saw that here when x is not equal to 0, then we got 0.95. So that means is that we're sort of biased. Our expected value of y, our prediction, is less than 1. Always going to be less than 1, at least on average. So it's going to be biased downward. Now in low dimensions with decently sized n, as shown here, the nearest neighbor really does kind of land near the origin. So bias and variance kind of stay small. Now recall earlier that we just showed that as the dimension or p grows, the nearest neighbor drifts further and further from the target point. So recall that d, which was our median distance, the d of 10, 500. So we have more samples that have their nearest neighbor at distance greater than 0.5 from the origin. So let's plug that in here. So at f of 0.52, which is literally the median distance away from the closest point to the origin, we get something like 0.135. So what is this telling you? It's telling you that at dimension 10, the closest point to the origin is going to be, pretty far away from the origin, and is going to make you predict a value of 0.135, which is much lower than what you want, which is 1. So this is very, very heavy bias, lots of bias here. So again, that's the nearest neighbor isn't so near after all, and is pulled towards the boundary. So the estimate collapses toward the tail of the function instead of its peak. Right, look at the graph again. We might, this point actually might be here, which is much farther away from the origin. And so we estimate a very low value of f, consequently. Okay, so here's two graphs to illustrate that point one more time. So in low dimensions, your closest point is most likely going to be near 0. And so your bias, sort of, the distance between your actual value and 1 here is not going to be so much. On the other hand, on high dimensional space, in this case 10, your closest point to the origin is going to be actually very far away, and so therefore you're going to predict not that high. In this case, it looks actually very close to 0. And so the bias, the distance between these 2 points is very, very big. Alright, so now let's assume that we know, or at least willing to assume, that the true relationship between y and x is linear. Now in this case, we know that it's not linear, but let's pretend that the true relationship is actually linear. So the output data is some linear combination of the input data according to our weights. And here we can also assume some error, some noise here, to be general. Now again, this is just a regular, OLS, assuming L2 loss. We can find a closed form solution for our weights according to our data in our sample labels here. Now, if we substitute the true expression here into this y value, let's see what we get. So what we get is that our estimate is centered around this true value, the true weights, plus some linear combination of the errors. So for an arbitrary test point x, or x0, so our predicted y value is equal to our point of interest multiplied by our estimated weights. So that's beta hat. Now, that's just plugging this in and we get this expression. So let's read it carefully. So our predicted value is the true value, x0 times the true beta, plus this linear combination of the error terms. So this is a weighted sum of all the noise across the entire training set, not just one point or a neighborhood of points. So let's run the same bias variance decomposition we just ran for one nearest neighbor, but now on the expected prediction error. Okay, we evaluate this as before, and of course, since the true value is still random, we have this irreducible error term here, but this gives us the full general bias variance decomposition. Now, here's the payoff. If the linear model is actually correct, so that's not always true, the linear model is correct, but let's, we're sort of imposing a structure onto the data. We're making an assumption. Now, If that's true, the bias term goes to essentially 0. There's no structural mismatch to be biased about. So that's kind of the whole idea right there. One nearest neighbor error was entirely biased, exploding as your dimension increases. A linear regression's bias doesn't grow with your dimension at all. Now, wait a second. Why is that true? Well, because our bias term here is this term here. Now, what is the expected value of y hat? Well, the expected value of y hat is just the expected value of this expression. The error term here, and so this whole term cancels out because it has mean 0, and so we're just left with this, this term here. And so, that gives you, this is f of x0. And so that's why the bias term goes to 0. Now, what about the variance? So this is where the weighted sum of all the noise comes from, a minute ago. Because the OLS averages information across the entire training set, rather than leaning on just one nearby point or a neighborhood of points, its variance only grows linearly in P, or dimension. So nowhere near, explosive growth we just watched in the K and N case. Now, I'm not going to prove this expression, but you can show that this is true. Okay, so let's stop and reflect for a minute. So, let's think about 2 weeks ago, where we said that the linear regression is high bias, low variance. K nearest neighbors is low bias, high variance, stated qualitatively. However, in high dimensions, K nearest neighbors bias explodes because neighborhoods stop being local and the data itself is pushed towards the boundary. Meanwhile, linear regression's bias, stays pinned near 0, assuming the model is right. Now, if the model is wrong, then the bias would be high again, which is why before we said that linear regression usually has high bias. But assuming the model is right, and its variance only increases linearly with P, because it pulls information across every training point, regardless of how spread they are, instead of trusting a collection of local neighbors. So that's the actual content of the Curse of Dimensionality. It's not that high dimensions are bad in general, it's that unstructured, purely local methods are the ones that really suffer. Now, the moment you're willing to impose structure, so linearity in this case, you sidestep the curse, almost. Now, we showed that again, the variance increases with dimension. So that's not always true. In fact, that's not true in general. But the curse of dimensionality is much, much less if you impose more structure on the data. So that's what we looked at today. So that's the real lesson underneath the curse of dimensionality. It's really a curse for methods that refuse to assume any structure at all about the underlying universe, not for the high dimensions themselves. So indeed, for the rest of the book, we'll look at other ways we can either deal with the curse of dimensionality better, or we can impose some other structure onto our data. So looking ahead, section 2.6 turns this into a general framework. So statistical models, supervised learning, and function approximation. Basically asking in general how much structure you should be willing to impose and why. So for that, I'll see you next week.